All right, so in this video, we're now starting to step into the world of statistics a little bit, and we're going to show you some properties of one of the statistics that we talked about in the last video. In particular, we're going to talk about the sample mean and its distribution and some of the characteristics that happen. And in fact, we'll start to kind of give you some predictors of how I can use the sample mean to predict a population value. And kind of give you a hint of what's to come. And then we'll also talk about a very important kind of rule of thumb called the law of averages, or the central limit theorem. We'll talk about that in this video as well. So without further ado, here we go. All right, so let's start off. We're dealing with the distribution of the sample mean. Okay, we're going to assume that our sample is a set of data points, x1 through xn, and it's a random sample from a distribution with a mean of mu and a standard deviation of sigma. So right off the bat, you should notice that that's a population characteristic and this is a population characteristic. Okay, so we're pulling a sample from a population in which I know the parameters that define it. Now, in practice, that may or may not be true, and that's one of the discussions we'll have to have in a later video on what happens if I don't know this value or I don't know this one. What can we do? And how does that affect things? One way to kind of think about this is that maybe you've been in an industry for many years and have a whole lot of historical data, and so you have a feel for an expected value or a variance or what you can expect, just based off of experience and historical data. That might be a scenario where this would probably work out for you. Okay, but what we can say is that if this is the set of data points, then the expected value of the mean of all of the data points on this, assuming they all have equal likely outcomes for us, okay, that the expected value of the sample mean then is the population mean. All right, so the sample, which is x bar, and the population, which is mu. Okay, and then the variance of x bar, the variance of the sample, then is taken as sigma squared divided by n. Okay, so this is kind of a corrective term based on the number of points that you have in the collection that you're looking at. Okay, and so if I take this and then take the square root of it, that gets me the standard deviation of the sample mean. Okay, so we've kind of come to the variance of the sample mean is that guy. All right, so that's sigma over the square root of n, and so that becomes one of the correctors. And it's this bottom guy that starts to become the term that becomes our correction factor for some of the problems that will arise later on. Okay, when I don't know one of the parameters, but I do know the sample. And one thing about a sample value, an x bar and a sigma x bar, you will always know those, because I can go out and I can collect all the data points. So you'll generally know those particular values. It's the population parameters that you don't. Okay, but if I know one, then I can predict the other. Okay, based off of these basic formulations. Okay, so basically, and one thing to note is that if the random sample is from a normal distribution, then x bar itself will also be normally distributed. Okay, which is kind of a useful little characteristic. All right, and so that leads us to something called the law of averages, or the central limit theorem. Okay, and basically, if n is large, x bar is approximately normally distributed. I mean, it's like, they talk about, like in baseball, the slump, that a batter is, going through a dry spell and is only hitting, 0.1 or, 100. Okay, well, at some point, they're always saying, well, he's due to break out. Eventually he's got to get better. Or whatever your application is, if you're not a baseball fan, basketball or whatever, there's always that belief that eventually that will come back and it will all average out in the end. That's the law of averages. That over a while, even though I draw a bunch of low values on one side, eventually I'm going to get the high values that will bring that average back to where it should be. Okay, that's the belief of the central limit theorem. Okay, now the rule of thumb is that it's that this will work is that n is greater than or equal to 30. Now, here's the idea of what they're doing with the central limit theorem. Okay, and where the power of this guy comes in. Okay. And basically, the basic idea is that the distribution of a sample mean tends to be normally distributed even when the distribution from which it came, meaning the average is computed, is decidedly not normal. All right, so what does that mean? And so I've got some graphs that I'll kind of walk us through. Let's suppose that I have my parent distribution for my random variable, okay, as being uniformly distributed in this case. Between 0, let's say 0 and 1, then the x bar would be 0.5 for this guy. All right, so if I take two samples and compute the mean based off of this distribution on it, okay, what happens is you now start to get a hump in the middle. Now, it doesn't look like a bell curve yet on this, but it does peak, and I have a low value on one end, a low value on the other, and then I'm likely to get one in the middle that's a little bit higher. Okay, now if I go to n equals 4, this diagram now starts to get a little bit more of a curl to it, okay, and it starts to look more and more like the bell-shaped curve. Okay, and then if I go all the way up to 32, okay, this guy is almost spot on to like within a percent or two of being a perfect bell curve. So, you know, say your batting average was down here, you know, and eventually you would expect to find the other side of the bell that he would get hot and, you know, eventually be able to, you could generate this bell shape on this, okay? That basically at n equals 32, okay, it approaches a normal distribution. And again, that's a theoretical concept on here, okay? It's not exact, and in fact, we usually just say if n is about 30, you're close enough. Okay, and so that's kind of our close enough category there. So anyway, that's kind of pictorially what the central limit theorem is doing without getting into a lot of the mechanics and a lot of the algebra that proves it. Okay, but it's kind of a cool idea to work with. So let's see what we can do with this and kind of show the influence of the sample size based off of this. Okay, so in our example, we're going to be looking at the breaking strength of rivets or bolts. Okay, and we know that the population of the material has a strength of 10,000 psi, and it has a standard deviation of 500 psi. And again, I may have, you know, a whole bunch of historical data that have generated this value. Okay, but this becomes important in engineering structures because obviously I need to know what this is to know what I can expect. Okay, but then we also want to make sure that I don't get one of the low ones and protect myself against that. All right, so we're going to define our random variable x as being the breaking strength. Okay, and then so what we've done is for n equals 40 samples, we want to find what's the probability that the average of my sample falls between 9,900 and 10,200. So it's kind of in that middle range. Okay, well, all we do is we basically go in and we apply our formulas that we learned. So the mean, or the expected value of the average is the same as the population value. So we're going to say that that's going to be 10,000. Okay, and then the standard deviation we said was the population standard deviation divided by the square root of n. Okay, and so I'm going to take 500 divided by, you know, the square root of 40, whatever that decimal value is. Now you notice that if I do a lot larger sample, say I did 1,000 on this thing, then what happens to the variance in the standard deviation of the mean? Well, clearly it's going to go down. If I put 1,000,000 on it, this guy's going to go to 0, which means that you're going to be able to expect this value dead on, if you will. Okay, now, because we know that these are normally distributed, I think I said that up above. If not, I should have. Okay, that x is a breaking strength. Nope, I sure didn't. So let's do normally distributed on mu and sigma squared. Okay, that will give us that piece. So if we know that we're normally distributed, then all we do is we play the exact same normal distribution games, but now I use my x bar value and those things. Okay, so all we're going to do is that we're looking for the probability that x bar is less than 10,200. That's the upper end. The probability that x bar is less than 9,900. That's the lower. And then I do my z coordinate to get into the standard normal form. So we're going to take 10,200 minus mu x bar, and then all that divided by the standard deviation of x bar, and so forth and so on. And I do the same thing for the 9,900. And when I convert it, my z characteristic is 2.53 for the first term, and it's negative 1.26 for the second. All right, and so if I go to my standard normal tables, you can quickly find that this value is 0.9943, and that this one is 0.1038 will get me that value. And I have a probability of between 0 and 0.89, 89% of falling within that range, of expecting that value to fall within the range. So now I'm trying to get kind of a predictor. I'm 90% confident that my mean will fall within that range. And that's not bad, but in structures, we like to be more like 99.9%. Okay, so this wouldn't be good enough. Okay, so you would have to figure out, well, what's my broad range? And in strength, then what you would do is you would choose the lower value to design for if you can get the probability that you're looking for. Use that as a minimum, and then you know that everything's above that with some certain degree of certainty or level of confidence. And again, the term confidence will have different meaning as we move into confidence intervals and some of the prediction intervals and stuff in the upcoming videos as we get there. All right, but just for good measure, let's run it again, and this time let's put 200 samples in this thing. Okay, so mu x is still 10,000. My sigma x now changes, and instead of being whatever that number was, okay, it's going to move down to 35.4. Okay, this one would have been what, like 40 or 50 probably, more like 80 or 90 on the one that was up here. But you can see that now it's a whole lot smaller, meaning we're a whole lot more confident that our bands are going to be a whole lot narrower. And so then I play the same game and I run through this, and you'll see that for that first 10,200 conversion, my z value is 5.6, and that's a massive number. Okay, and then my lower bound one is now 2.82. Okay, and so what happens then is that this guy's off the charts, which basically means on the high end, which means that that probability is 1.0, that everything is less than him. Okay, and then if I take the number of 2.82, we're getting into a really negative number, but we're still on the chart. The probability of this is 0.0024. Okay, and so if I do that, the difference in is 0.9976. So we're at 99.7% confident that if this is my data and I've done this sample 200 times, 99.7% of the time I could say that the data would fall within that range, and I'd be comfortable to say it. Okay, so now here's the payoff, is that basically more samples in means more certainty, right? If I jack this thing up to 1,000, that number gets even higher, gets even closer to 100. Okay, but whereas if I start to skimp on it and I go down to like 20, then this number changes, and then we also violate the assumptions of the central limit theorem. So we'll have to do something different. And we'll talk about those in the coming videos, where what happens if I don't have n equals 30? Because at the end of the day, n equals 30 is kind of the magic number. Okay, if you're above this limit, this technique will work for you. But if you start dropping below this, we have to come up with some different distributions. Our assumption about a normal distribution isn't valid anymore, and we'll have to come up with new techniques. And that will lead us into our discussions in the coming videos as we start to move through there. Okay, now, again, so it seems easy. Well, I'll just run the numbers up and test a whole lot more, and then I'll be really confident in my effect. But what happens if each one of these samples costs you $1 million, right? There's a big difference between 40 million and 200 million, right? As from an economic standpoint. So we want to pick these so that we get the information that we want, but we don't have to spend way too much money performing all these testing or all this quality control, or maybe each test takes you 4 hours to do. Well, 200 tests versus 40 tests at 4 hours each, that's not insignificant. You got to pay somebody to do that work. So that's kind of the basics of what's going on as we start to kind of look at, this distribution of the mean. I mean, at the end of the day, it's very, very simple, right? All we're doing is we're coming back and we're taking advantage of those basic equations, right? And basically altering my function, but this is what we believe the distribution in the mean is going to look like. Okay, and taking advantage of the central limit theorem along the way. So anyway, short video, I know, but this one's important enough that I thought I'll just kind of keep it on its own. Hope it made sense to you. As always, if it didn't, or if you have any questions, leave some comments down below. We would greatly appreciate it. Like the video if you would, and of course, subscribe to the channel if you haven't already. So anyway, thanks for your time, and have a wonderful evening. See you all next time. Happy engineering.